Any questions about that? Okay. What we're going to do next is we're going to show the utility of this. How can we look at systems where we aren't at 298K? How can we move beyond just that single temperature to actually measure these changes in state functions, and how will that actually benefit us? After your Quizlet next week, what we're going to do is we're going to show there's a relationship between CP and CV, which is weird because it falls out of mathematical magic, and it's cool because there is just a straight relationship. So if you know one, you can figure out the other very easily. Okay. So let's talk about the temperature dependence of heats of reaction. Temp dependence delta H. Okay. So far, we've only considered looking at heats of reaction at one specific temperature where the temperature is not changing. What about if we do want to look at a system where that temperature is changing? Ooh, tell me to shut up. There we go. We want to look at delta H reaction with changing temperature. To do this, we're going to consider a system being heated from some temperature T1 to a new temperature T2. Delta H. How does this relate to a constant pressure heat capacity again? What do we have to do? Integral of what?
CP times 32.
Yeah.
Initial and final temperatures.
Yeah. And our initial temperatures T1 and T2. Okay, we can actually break this side apart into the enthalpy of temperature 2 minus enthalpy of temperature 1 is equal to this enthalpy. You might be asking yourself, why are we doing this? We have some reference temperature, let's say it's 298K, and we have a new temperature, some other one that we want to look at. We can use this as a reference and figure out that change in enthalpy later on. So we can manipulate this Did I do that right? Math. Nope, should be a plus sign. Right? Yeah, anyway. All right, we're just going to change this to a reference state. So we're going to look at a heat of reaction, so a change in a heat of reaction at some temperature, new temperature, minus the heat of reaction at our initial temperature plus this integral. This is known as Kirchhoff's law. Oh, I'm sorry, there should be a delta in here. We'll put a sub M too. Let's make that more complicated for you. Where this delta Cp M is molar heat capacities, we're looking at the change in molar heat capacities. So we just look at products minus reactants. Okay. Don't really have enough time because we're already over time. But what you can do is you can look up these molar heat capacities. You can look at the stoichiometric ratio associated with them for a balanced equation, and you can just plug in these values. Okay? Your daily problem has to deal with utilizing this information. Okay? Are there any questions right now?
What does stand for?
That is molar heat capacity. So just like you would have molar volume, this is on a per mole basis. So you might need to multiply it. It really just depends on what you're doing up here. Okay?
Will this stuff be in our episode?
Yes. Know how to do this thing. Okay? It's really not that tough. Your daily problem will cover how to do it, or at least give you an example of how to do it. And there are lots of examples and work along examples in your book and in that David Ball book over there that show you how to do this. Okay? If you're not sure what you're doing, come see me. Okay? Any other questions?